right, last time we were talking about this concept called non-determinism, and I want to go over that one more time just because it's a very strange concept coming from a deterministic world. I guess first, does anyone have any questions or concerns before I dive into the material? All right, so everything you've ever done is deterministic, everything you've ever programmed, because searching is a necessary part of computer science. You don't know what the right answer is, you need to find the right answer. But you can imagine if you knew the right answer, how long would it take for you to verify? Or if someone told you this is the answer, could you verify that in polynomial time? So NP is this interesting class of languages that can be solved non-deterministically in polynomial time, and non-determinism, again, I like to think of it as that concept of infinite parallelism, where we can, as a process, fork an arbitrary number of child processes, and we're not limited in that. In reality, we have a CPU with so many cores, and we can only fork as many children, as many parallel processes as we have cores available for that. So eventually there becomes a problem that requires more child processes running at the same time than we have cores. And so this falls apart. We have to do something sequentially. We have to schedule these cores so that when one finishes, another one's beginning, and et cetera. But if we had an infinite number of cores, we could allow for anything that could be done at the same time to be done at the same time, regardless of how many different processes we had running. And that's kind of the idea of non-determinism. You can also think of it as the verification. You can also think of it as, rather than having to search, you just guess, and your guess is always correct. This was the way that it was explained to me, and it made no sense at first. The way that I've come to understand it, I think works better for me, but I like to present all three of those ideas for whatever makes the most sense to you. So whenever we have non-determinism, there's always a potential set of next steps. When we use the idea of cracking a password, there are a sequence of next steps that could be whatever character I could enter next. We could either assume that we enter the right character, that someone has told you their password and asked you to verify that their password works, in which case you know what the next character should be based on what they told you, or the concept of infinite parallelism. We're going to have some number of children, each of which is trying a different character in that position. And by the time we have an exponential number of these processes running, we can determine the password in linear time. So why do we care about this? There is an interesting class of languages that is called NP-complete, where we can prove that there is it's in NP, so it's verifiable in polynomial time. If we had infinite parallelism, we could solve the problem in polynomial time. However, the best known solution is deterministically is exponential. So deterministically exponential, non-deterministically polynomial. However, a giant open problem in computer science is whether this class of languages, the class of language that is P and the class of language that is NP, is the same. This is the open problem that we can't prove and we can't disprove. In math, there are true statements that we can't prove. Gödel's incompleteness theorem tells us this. I'll go over this more in compilers for those of you who are interested. But there are limitations to math, and it took up until close to 100 years ago to figure this out, that there are true statements that math cannot prove. One interesting version of this is the twin primes conjecture. Has anyone heard of the twin primes conjecture? So 3 and 5 are sequential odd numbers that are both prime, as are 17 and 19, this continues as far as we are aware. You look at numbers that are greater than 1 billion, you will find 2 consecutive odd numbers that are twin primes. You look at numbers that are greater than 1 quadrillion, you will find 2 consecutive odd numbers that are primes. The question is, does this go on forever? How would you know that? How could you answer that question?
Have like a cap on far up as you can.
Yeah, right. So numbers go on forever in the positive direction. So we can just keep finding twin primes. But imagine that we had gone over the next quadrillion numbers and hadn't found a twin prime. Could we conclude that we found the last twin prime? We have to keep searching. And in fact, we would never know that we had searched far enough to be able to conclude that we've seen the last twin prime. So there's no way to know or answer that question. It turns out that this is one of those unsolvable problems in math. If the answer is that they go on forever, there's no way we would have to prove by some relation of these twin primes what the relationship is. But as far as we can tell, the relationship is arbitrary. If there is an endpoint and that there's a last twin prime, after that, how would we know without searching and searching and searching, but that search never ends. So we'd never be able to show or prove that there is a last twin prime. So math has some limitations. There are true statements. One of those two is true. There's either a last twin prime or twin primes go on forever. One of those two statements is true. But math isn't going to help us answer that question unless we can find an underlying representation and prove that that representation leads to a pattern of twin primes. If there is no pattern, like pi is an infinite number that does not repeat as far as we know. It's another unsolvable question. We keep dividing and finding more digits of pi. We're up to trillions. I think we're close to a quadrillion digits of pi at this point. There is no repetition, and it hasn't terminated saying, that's it, that's pi. It stops there. Does pi ever repeat? Is pi a rational number? We don't know. As far as we know, it is irrational. But again, we have no proof. So it's a very similar idea here. Are these two language classes the same or are they different? Yeah.
How would an assignment look like for this topic? Like, are you gonna actually have us, does the process stop?
Kind of. So I'm going to demonstrate how we add problems to this set of problems. We're going to call this NP-complete set of problems. Because we don't know the answer to this problem, we can pose a very interesting question, which is, if P equals NP, what does that mean? If we could ever conclude that these language classes are the same, then what are the class of problems that become easy? So we want to add to that list of problems that are currently hard. But if we could say this is true and ever conclude this, then all of those problems would become easy. So yeah, class of algorithms, NP-complete, that is proven to be in NP. There's a polynomial time verification algorithm, but are not proven or disproven to be solvable deterministically in polynomial time. The best we can do so far is exponential. However, there is a polynomial time conversion algorithm into another NP-complete algorithm, which means that if we could ever prove that a single one of these problems in this NP-complete class is in P, then we could say that every one of them is also in P because we could convert between those problems in polynomial time. So if I solve this one problem in polynomial time, I could convert this problem into another problem in polynomial time. And then that one is solvable in polynomial time because something polynomial plus something that's polynomial, you solve one problem, you convert it into another problem that takes now polynomial time. So by solving one problem, we've solved them all, which is incredibly powerful. But we've been unable to do that. We can just grow this class of languages that says that these are all about equally difficult. We can convert between them. So the big open question is just any algorithm in NP-complete. If we can prove there is a deterministic polynomial time solution to any of them, we've determined there's a polynomial time solution to all of them. Do a little bit of work, get a massive benefit. However, there are many assumptions we make in the computer science industry that P is not equal to NP. The entire security of the internet is built on the concept that P is not equal to NP. If we ever prove that P equals NP, delete everything. Unplug everything. Nothing is secure anymore. The way I like to visualize NP-complete algorithms is as a graph. If each vertex is a different problem, then each edge is the process by which we could convert from one problem to another. So we add problems to NP-complete. So we can't solve them directly, but we could create an eventual solution to this problem. If someone solves any problem in the NP-complete set, then by adding a problem to NP-complete, you're laying the groundwork for a solution to that problem whenever anyone solves one of these problems. And that's what an assignment is going to look like. It's basically, here is a problem. Is it in P or is it NP-complete? If we can prove that it's in P, great. It's easy. We can solve it today, deterministically in polynomial time. If it's not in P, is it in NP-complete? If it is, then we can reduce it to another problem. We can show the translation from one problem to another problem in a way that adds it to this list of problems that get solved whenever one of these problems gets solved. And maybe one problem that we add to this list is just easier to solve than the others, and we can show that we can solve it. So it's a very open problem, a very interesting problem in theoretical computer science. My personal opinion that you should add probably very close to zero weight to, because I'm not directly in the middle of this research field, is that I don't think that P is equal to NP. I don't think there is an efficient solution to any of these problems. But no one's been able to prove it. So I'm just asserting that with no evidence. So big open problem. There is an open, this is becoming less and less valuable over time, an open $1 million prize if anyone solves any one of these algorithms. People have been trying for decades.
I think a professor here would disagree.
Possibly. I think the most common conclusion is that P is not equal to NP. Just intuitively, that's my takeaway. But yeah, computer scientists can be split on that. And I mean, the arguments, you can't have any validity there with your arguments. I think this, I think that. Prove it. So if you want to actually say I'm right and you're wrong, show it. I'm not confident in my ability to do that. So I'm not going to argue with anyone. If you say P equals NP and I think that's true, great. Prove it. So just like adding a vertex to a graph, you would just say, all right, I want this vertex to be connected to this graph. So I just have to define an edge between this new vertex that I'm adding and an existing vertex in this connected graph. It doesn't matter where you connect it. You can connect it to any other vertex in the graph. You just have to add this vertex to a connected graph by drawing an edge somewhere to some other problem that is proven to be an NP-complete. So to do that, we need a polynomial time conversion algorithm. We need to be able to say, I can take any instance of the problem that I want to add to NP-complete, and I want to be able to convert that into an existing problem that is NP-complete. So this is called a reduction proof. You're going to reduce one problem into another. The basic idea is that we take an instance of the problem that we are trying to solve. We apply the reduction algorithm to it. That gives us an instance of the target. And then we can use the polynomial time algorithm. The basic idea is now, if this algorithm can be shown to be in P, then this, we have a polynomial time conversion algorithm. We take this problem instance, we convert it polynomially into this, and then someone solves some polynomial time solution to one of these NP-complete problems, then we can either answer yes or no from there, and this entire process is polynomial time. So we're laying the groundwork for an eventual aha moment. Does that make sense to people? Any clarifications I can make to that idea? Think of it like maybe converting between, if there's an easy solution in Java to a particular problem. If we could, and I can't solve the problem in C sharp, but I can come up with a translation between any Java program and any C sharp program. If there's an easy solution in Java, then I would just apply the translation algorithm to translate the Java program into a C sharp program, and there's my solution. I don't have to invent it in C sharp. I just have to invent it in Java and invent the conversion algorithm of Java to C sharp conversion. But of course, the problems we're going to tackle are not quite like programming languages. One thing we should talk about as we do this is the concept of why is polynomial time this big deal? Getting things into polynomial time. Because if we do that, there are certainly some polynomial time runtimes that are intractable. So something like n to the 100th. That's not a tractable problem. That does not scale well at all. But if we look at actual practical problems, we find that very few of them run in significantly more than quartic or quintic time. That's n to the 4th and n to the 5th, respectively. We find that in practice, once we take a problem that the best solution used to be exponential and we find a polynomial time solution, then there are tons of optimization techniques out there to take a polynomial time solution and find a faster polynomial time solution or a better polynomial time solution. So once we lay the groundwork for mapping a problem to polynomial time, optimizations happen from there very easily and quickly. So practically, we're very focused on finding polynomial time solutions because it opens the door to tractable, solvable problems. So nothing that I've ever seen runs an n to the 100th time. You can definitely come up with something that doesn't do anything useful. You could write a 100 nested loop. And I don't know what each of those loops are doing, but okay, I can actually think of one. That would be a 100-dimensional machine learning problem. You're going to look at every possible value of every one of those 100 dimensions. You would need a 100 nested loop. No one's doing that, though. All right, so how does one do this? How does one convert one abstract problem into another abstract problem? And it's worth noting that really all algorithms are functions. This is how computer science is an applied math. Whenever you write an algorithm, all you're doing is writing a conversion function between the inputs and the outputs. For all inputs, here is the process we use to convert the inputs into the outputs. It could be a sequence of steps, but really that maps to a mathematical function, or if it's just discrete inputs and outputs, then it's a relation. It helps if you can convert the problem instances into binary, because then you can relate them as a number. You're converting one number into another number. And that's all a function is, right? Is converting one number into another number. Y equals something x. You have some function that converts one input into an output. You feed in x, you get a y. That's all any program you've ever done is actually doing underneath the hood. It gets converted down into machine language. And then what you have is an abstract representation of a function. So to do this, we need some kind of abstract view of the problem. We need some way of saying, okay, well, how can we break this down into some binary problem? So as an example, Dijkstra's algorithm is a relation between an input triple, which is a graph, a starting vertex and a destination vertex, and a path or list of nodes that is the shortest path to get from source to destination. Any thoughts on encoding that? What would that look like? How would a graph be represented as just binary?
one, just having like a whole bunch of zeros and then just a one where vertex is. The ones where there's an edge.
Yes. We could list the vertices in some capacity. We could either name them and then use an existing conversion like ASCII, where we convert the string to a binary representation. We could then build some kind of Huffman code tree to convert that into something that's smaller, a smaller representation, and then we would have some number of vertices that we could then say, that's a vertex, that's a vertex, that's a vertex, that's a vertex. Then you have some separator that's not read as a sequence of binary that's not any vertex. And then after that, we just list the edges. So we're going to have a vertex that's a source, a vertex that's the destination, and an edge weight. And we build some conversion for that. And you would just have a list of, here are all the vertices, here are all the edges, and some way to parse that very similarly to how we looked at Huffman codes. And we could just read binary as a sequence of letters that represented letters, but it was just zeros and ones. Very similar. We could have an encoding of a graph that's just a bunch of zeros and ones, but maps to a specific graph. If you have a way of converting to and from that representation, then you could feed in how you visualize a graph in a JSON format that is coming today, I guarantee it. Talk to the TA yesterday. He has it coming. And then you would do the same thing for a starting vertex and a destination vertex. And then you would have a function that maps that long string that represents the graph, the starting vertex, and the destination vertex to the concept of a path, which is just going to be a list of the existing edges. So the input are those three problems, the three components, and the output is the edges that are the path. And now Dijkstra's is just the infinite mapping of graph, source, destination to shortest path. That was complicated. A relation for just the natural numbers is pretty straightforward. This is what we use in binary for numbers anyway. We want to be able to represent negative numbers, then we need 2's complement. But if we're just looking at positive numbers and zeros, we can just use regular binary. ASCII is an encoding of character to integer. It's a way of taking in a character and having an integer representation of that. So these encodings already exist in things that we are doing, but this is a much more complicated version of that encoding where you need to define what the encoding is so that you can map the problem instance. But the difficulty in a reduction is going to be saying we need to take one encoding and convert that into another encoding. We're going to take the problem encoding of one problem and convert it into the encoding of another problem. If you want to take complex objects, you can concatenate encodings of each of its components. That's what I mentioned with the Dijkstra's algorithm with the graph. A graph is just a list of vertices followed by a list of edges. So we would take each of those components and we would break that down into each of those components. And then each of those components are going to be a string or an integer. And a string is made up of multiple characters, which use ASCII as an encoding. So we can, just like we build objects out of other objects and primitives, we can build encodings out of other encodings. So we can encode arbitrarily complicated structures. We can encode programs. This is how compilation works. This is how you convert a program that you write in a language is reasonably similar to English and logic, and it gets converted down into ones and zeros that a computer can run. The fact that we can abstract this to the point where you can think logically and not in terms of ones and zeros is pretty amazing. That all of that work has been done by past geniuses so that we can just work in a programming language. But there are still many theoretical concepts out there that rely on our ability to understand how these kinds of encodings work. So let's take a look at what we need to do here. This is where things get a little bit complicated. To add a problem to the existing set of NP-complete problems, we first have to prove that there is a single NP-complete problem. We need to add the first vertex to the graph. Once we have the first vertex to the graph, the problems become easier because we can reduce down to that problem. So we need to prove that some algorithm is NP-complete. And we're going to look at circuit satisfiability to do it. It's called circuit sat. So we have a Boolean circuit. Think back to, for those of you who've taken electrical engineering 160 or computer science 260, what a Boolean circuit is. We have AND gates, OR gates, NOT gates. All their more complicated gates are just made out of those components.
You talk about digital circuits class, aren't you?
Yep. So all logic can be broken down into ands, ors, and nots. Everything else we focus on is just a combination of that given another title. So is there some combination of inputs that causes the output to be 1 or true? Let's give you an example. Here's an example of a Boolean circuit with an instantiation. The input wire x sub 1 is 1. The input wire x sub 2 is 1, and the input wire x sub 3 is 0. If this is the case, we pass through ors, nots, and ands, and we see we can feed this forward through this Boolean circuit and find that the output wire to the final AND gate is 1. If there exists some combination of these inputs such that the output is 1, we call the circuit satisfiable. Take a second and do that logic in your head. Make sure that this is correct. I guess I should ask, have we seen these kinds of circuits before? Maybe a show of thumbs, just how easy is it to figure out what's happening here?
Like, once you told me what they own.
Yeah. So this is an OR,
Yeah,
this is a NOT,
and
this is an AND.
both of those are OR gates, and the last one is not yet. Both of those next ones are OR gates, and the last one is an AND gate. And
So yeah,
very well.
when we feed in this 0, this NOT flips it. So this outcoming wire and where it splits here, all of those are the opposite of this 0, which is a 1. This OR is going to be a logical inclusive OR. It's going to say 1 or 1. True or true is true. So the output wire is going to be a 1. When this 1 comes into a NOT, every outcoming is a 0. 0 or 1 is a 1. 1 and 1 and 1 is a 1.
Yeah.
So this circuit is satisfiable because there exists some combination of these inputs. How did we know that it was this combination of inputs? Because I told you. What would it take in order for you to show that that a circuit is satisfiable? What is a brute force way of doing that? Trying every combination. How many combinations are there going to be if we have n input wires?
Two,
We actually don't need it here.
well, let me think. And the 3 inputs, bunch of combinations, would that be 8?
Yeah. How do we get there? What's the formula that gets us to the 8?
2 to the end?
2 to the n. Yeah. It's exponential. So unless we can do something better than this is not going to scale particularly efficiently. So an NP-complete problem would be one that says, okay, well, there's no better way to do this than to check them all. And to illustrate this, walked up on me. I have one for you to try.
Which is that one to the right, and
Yeah.
that is, let's see.
So, how much work does it take to determine if this circuit is satisfiable? Play the role of the computer here and see if you can find a combination of X1, X2, and X3 that lead the output wire to be a 1.
It's gonna be fascinating. Really fascinating. It's the output.
Go ahead and try it out. Yeah. You don't think there will?
No.
What makes you say that?
The not on X3, it has to be a 0 to specify on and 0, and it goes up to the not gate. A, or it gets not in there, wonder that not gate becomes 0 because it can.
Yeah.
Yeah, I'm in agreement. I was coming closer to that thing.
Yeah, this has no solution. This circuit is not satisfiable. And because you can see, you can apply logic, and this is one reason why the human brain is amazing compared to what we have to think about in terms of coding an algorithm for a computer. We can see that this negation feeds into this and, so this has to be a 0 in order to feed this in to be a 1. But this then also leads to a negation that leads to an and an and. So this has to be a 1. When we feed this in, this has to be a 0, which means that this and cannot be satisfied, which means that this wire cannot be satisfied. And since this is an and, every wire has to be satisfied in order for this output. But also recognize how small this circuit is. How much work would it take if this scaled to be larger and larger and larger? How much parallelism would you have to be focusing on? This gate leads to this gate, leads to that gate, and this gate, and that gate. You need to consider an arbitrary combination of the gates in order to be able to show or prove, and think about writing an algorithm to do that. Our human brain can very quickly isolate the most likely path that is going to lead to a contradiction. A computer does not have that level of parallelism. You're using a limited form of parallelism when you solve a problem like that, which is also cool to map onto a computer. But the human brain doesn't scale its parallelism infinitely. If I gave you a large enough circuit, you wouldn't be able to say anything meaningful about it. But it's awesome that we can say something like that about a circuit that's this small. Human brain is amazing. We are so cool. Does that make sense to people? You can try all 8 combinations, and none of them will lead to the output wire being 1. But algorithmically, there's no easy way to do this that we have found. But how can we prove that there's no easy way to do that? How can we add it to this NP complete? So let's spend a little bit of time thinking about how could we encode this problem? Any thoughts on encoding this? I'll give you a hint. This is not completely out of left field. This is something that I have prepared you for in some capacity.
Arbitrary combination.
We want to encode it as something that encodes to binary. Basically, we want to turn this problem into a data structure or a something that maps down or could be broken down into binary.
Okay. Yeah, there's also something else. It feels like if you're going to try to solve a problem, it involves some sort of, I don't know, not sure if I'm thinking about this correctly, but I am thinking of mildly greedy assumption for this one. But that is mine.
That's good. That's good.
Alright, so. So we need to put it into data structure. Well. Yeah. There we know being.
I hear a lot of tree. If we do tree, here we would have something like, we would have a child, we would have children, and then they would merge together. Is that something that we can do in a tree?
Not really.
No. That is not allowed in a tree. It's a great starting point, though.
Yeah, it's
You just. Pass it along.
yeah.
Graphs.
Yeah,
Yeah,
because-
that's exactly what we want to do.
You can't close those things, but remember what what it said during graphs? Yeah. All trees are graphs, but not all graphs are trees.
So we can map a graph to a binary string, exactly as I talked about earlier today, by listing all the vertices, listing all of the edges connecting the vertices, and then we just break all of that down into binary. We don't need to know exactly how that happens, just it's good enough to know that that is possible to do. The next important thing to talk about is the size of the encoding as a function of the number of gates, because it's not going to be good if we have an exponential size encoding. We have a problem, it's already going to be an exponential complexity problem to convert it into an encoded form if the length of the encoding is exponential with respect to the number of gates. So what is that size of the encoding? It's going to be polynomial because we can name each vertex, and as long as we're not coming up with ridiculously long names for vertices, we can optimize that down into the shortest name that we need. We're going to start listing vertices by single characters or even single numbers representing an association of this is that vertex. Make that as small as possible, and that will be polynomial in the number of vertices. Same with the number of edges. It's worth also thinking about, it's one thing to just think about, this is a fun problem to try to solve, but are there real world implications to solving circuit satisfiability? Imagine that we had a polynomial time algorithm for determining whether the output of a circuit is 1 or 0. What would that lead us to be able to do? Maybe this is more of a question for electrical engineers, but
Yeah.
it has real value. Does anyone see what you might be able to do if you could do that?
Yeah, I think
What if something is always off?
that
What does that mean?
means that
Yeah,
yeah. That's
yeah. When we design circuits for problems, imagine looking at a sub-circuit. If that sub-circuit is always off, we can get exactly the same value, exactly the same performance out of that circuit if we remove that subcomponent, which makes it more efficient.
Yeah.
Yeah, we could optimize circuit design in polynomial time if we could solve the circuit satisfiability problem in polynomial time. It would be trivial for any circuit to make a circuit optimized. That's a big problem in electrical engineering. There are people who do that for a living. We could take their jobs the same way that AI is taking ours.
I hate hearing those words.
I know, me too.
But I'm also hearing how AI is currently, a little bit of decline, I hear. But I don't know how true that is.
So yeah, we can determine whether sub-circuits are necessary or unnecessary, which leads us to incredible hardware optimization. Screw you, NVIDIA, we make the profit now. So yeah, in a large circuit, if there's some sub-circuit that's unsatisfiable, we remove that sub-circuit and replace it with the constant that is 0. We just take an entire sub-circuit, replace it with one wire. Way faster. So what we're going to be doing, and I probably don't want to start this with how little time we have left, I can at least talk about it a little bit, is we want to go and prove that this is NP complete. If we could solve any of the other problems that we can add to NP complete, we can optimize circuit design. We can optimize hardware efficiency. That's a pretty exciting, like that would be a groundbreaking achievement if we could do that. In general, we have two steps to how to do this proof. We need to, one, prove that the algorithm is in NP. And then we also need to prove that the algorithm is NP hard. That's a new term. It just means it's at least as difficult as every other problem that is in NP. So it's at least as difficult, I guess I should say, as everything else that's in NP complete. It's kind of exponential complexity or worse in the worst case. So NP hard, every language in NP is polynomial time reducible to the target problem. Any given NP algorithm would be reducible to circuit satisfiability in polynomial time. So we want to prove that circuit satisfiability is NP. We're going to do that by inventing a polynomial time verification algorithm. Basically, if I tell you what the satisfiable values are, could you tell me whether that circuit is satisfiable in polynomial time? Going back to this problem, if I give you 1, 1, and 0, is it polynomial time to tell me that this answer is 1, polynomial based on the number of circuits that we have? Or if you had infinite parallelism, and you could say, all right, well, this could be 1 or 0, so I'm going to fork two children. One of them says x1 is 1, one of them says x1 is 0. I'm going to fork two more children, one of which x2 is 1, x2 is 0. So you have 8 total children running at the same time. So you'd be solving each one of these problems at the same time.
Yeah.
If you had 8 child processes, then it's the same as the verification algorithm, because the 8 child processes would all run with the same time, where if I told you what the answer was, how long would it take for you to verify? That's why that's the same, that's an equivalent way of thinking about it. All right, we'll come back tomorrow and talk more about how to actually add this problem to NP complete. Hopefully this is at least somewhat intriguing.
It is very intriguing, actually. Oh God, I am so okay.